So I've been presented with this challenging task of presenting a theoretical paper as the last talk of the conference. I'll try my best to not put everyone to sleep. So this is a joint work with my colleagues Ganesh, Shweta and Rohit, and my supervisor, Professor Y. Nadali from Indian Institute of Science. So I'm going to talk about the analysis of Thompson sampling for stochastic sleeping bandits. So I guess you already have sort of a primer on several bandit frameworks, but I'll briefly go over it. So essentially we have a set of bandit arms. So what are bandit arms? Like if you go to a casino and you see a gambling machine, you essentially pull their arm and you get some sort of reward. So although you don't know how it's generated, there's usually a distribution behind every machine which is generating those rewards. Now imagine a scenario where you have a set of bandit arms or like a set of machines, and you want to ideally pull the arm of the machine with the best reward distribution. So this leads to a sort of exploration-exploitation trade-off. You want to sample different arms, get an estimate of the reward distribution, as well as exploit the knowledge that you have learned already, right? And in the process, pull arms sequentially such as to maximize your reward. Now, what is the sleeping multi-arm bandit setting? When we try to model real-life scenarios as a multi-arm bandit problem, it's a really dynamic scenario. You don't always have a fixed set of arms, or let's say a fixed set of advertisements, or a fixed set of agents whose reward distributions you want to learn, right? So what you do have is that each time step you have a subset of the total set of agents available. So you can think of it as some of the bandit arms are sleeping at points of time, so you can only pick from among the ones which are awake. That is the simple sleeping bandits assumption. It's essentially a generalization of the classical bandit setting. So we have already seen the application of bandits for advertisement, ad options. So in this scenario, the set of ads that you can display on your website might change over time. Another new application of multi-arm bandit settings would be network routing, where you have a network of computers, routers, hubs and stuff. So you want to, like, you can assume that there is a stochastic distribution of the delay through each path from one source node to the target node, but you don't know that distribution beforehand. You can learn on the go by sending packets to each path and exploiting the knowledge that you already have. But some routers might go offline in between, and essentially you are left with only a subset of paths, or some new nodes might join the network at some point of time. So as you can see that the set of bandit arms are essentially quite dynamic, and so I guess the sleeping bandit framework applies to the real world much more. So as part of our work, it's mainly a theoretical result. We present a logarithmic regret bound for Thompson sampling for the sleeping multi-arm bandit problem. I'll get into what exactly we mean by regret in this particular setting in the next slide. We also show a dependence on the availabilities, like the sequence at which arms are available at each point of time, how that influences the regret of our algorithm. And finally, we show through simulations that our theoretical findings agree with our empirical findings. Okay, so as part of our modeling, we assume that the union of all available sets of arms at each point of time, like in total there are k possible sets of arms. We assume that the rewards are distributed Bernoulli with means mu I. Although this is a particular scenario, this can easily be extended to rewards in general, reward distributions with support in 0, 1. But for the sake of analysis, we assume that it's Bernoulli here. We assume that the first term, without loss of generality, we assume that the first term has essentially the highest mean reward, and the second term least, and so on. So we represent by AT the set of available arms at time instant t. And for the sake of analysis, we assume that there is a time horizon t, like that is the number of times an arm is pulled throughout the algorithm. I'd like to point out that the algorithm does not assume that t is known beforehand. That's only for the finite time analysis. It essentially works for infinite horizon problems as well. So how do we measure the performance of any algorithm in this sort of setting? Right? So, like I said, AT represents the availability of each arm at time t. Now consider all the availability sets at each point of time from A1 all the way up to A capital T. So let us call that our availability sequence. Now at each point of time, depending on the available set of arms AT, we know that the optimal choice of arm would depend on the actual mean reward of that arm, which we do not know. We denote that optimal arm as IT star. So now, given a particular availability sequence, we define our regret as the expected difference between what we could have achieved with complete information and what our algorithm actually achieves, right? So this is for a given particular availability sequence. Now, since we do not make any assumptions on the availability of our algorithms, that is, we do not assume that availabilities are also generated stochastically, they are arbitrary in a sense. So in the worst case, that is adversarial availabilities, we get overall regret of our algorithm, which is just the max of the regret obtained over all possible sets of availabilities. Okay, so our algorithm is essentially a very trivial extension of the classic Thompson sampling algorithm, where we maintain a beta prior on the reward distributions of the arms, and at each point of time we obtain a sample theta IT from that beta prior and use that as an estimate to estimate the mean reward distribution and choose the arm with the highest Thompson sample. And based on the reward that we obtain, we update our posterior distribution and go on. So we initially start with the uniform distribution, which is a beta 1-1 distribution. So one thing to mention, unlike the previous two settings, this setting is context free. Like the reward distributions do not vary from context to context, and the rewards that you obtain are immediate. There is no delay between each reward. Yeah. So the main result that we provide in this paper is regret bound, availability specific regret bound, which shows that the regret of the algorithm is actually logarithmic in terms of the number of times each arm is available. So by AJT, we denote the number of times each arm is available till time t, and the rest are problem dependent constants. So this is in accordance, like this is similar to the sort of regret bounds we would find for classical bandit settings. So if we consider the classical bandit availability, that is all arms are available, when AJT is equivalent to t, we actually arrive at the adversarial availability setting, which gives us a logarithmic regret, and this is actually a tight bound, as we can see from the below lower bound, which holds for any algorithm for the sleeping multi-arm bandit setting. So it's a bit of a involved proof, so I'll not go into all of it, but I'll try to give some key insights into how the analysis goes. So we make the assumption that arm 1 has the best reward distribution, arm 2 has the second best, and so on. So essentially, if we take two indices I and j, where j is greater than I, and we assume that some arm in the same set 1 to I is available, then essentially if we pull arm j, we are making a suboptimal choice, right? So we denote the number of times this event occurs by nijt. So we ideally want to get a bound on the number of times this event occurs, and that will essentially lead us to a regret bound. So one of the key lemmas that we use in order to obtain this bound is that the lemma shown here. So here in essence what this lemma is saying that if some arm I is optimally is the best available arm W at a number of times, that is, it is among the available set of arms, as well as it has the best reward distribution among these available arms, that is represented. So if that happens W at a number of times, then the number of times that it is actually chosen by our algorithm, which is denoted by NIT, cannot be too less. So the more number of times our arm appears optimally, eventually our algorithm will start to converge to choose that optimal arm. That is essentially what our lemma tries to take. So the main challenges involved with analyzing Thompson sampling is that it's randomized. So it's not very trivial. like Thompson sampling was first proposed in 1933, but a finite time analysis for it was not provided in 2012 by Shipra Agarwal and eventually by Emily Kaufman, who showed that the repeated bound of Thompson sampling is asymptotically optimal. So unlike their work, which deals with the classical bandit setting, we have to zoom into what's actually happening according to the availabilities. So if you look at the original timeline, that is the sequence of all time steps where our algorithm is pulling an arm. Now consider a particular arm I. So the blue squares actually denote the time steps where arm I is available. It's not available at all points of time. So if we take just those squares, we essentially get a different timeline which denotes the time steps where I is available. So we call that the I available timeline. Now when I is available, there can be two scenarios. Arm I can be the optimal available arm, or it can be essentially there is some arm greater than I is available. So what we essentially want to show that when I is available as the optimal arm, but yet it's not chosen, which is shown in the final timeline known as the I optimal timeline. So what is the expected length of the interval between which I is present optimally but not chosen? So by bounding that, we essentially show that our read rate is logarithmic. For this, we essentially employ mostly a lot of concentration inequalities, and other than that, it's fairly straightforward. So I would like to mention that this proof sort of heavily relies on the techniques used by Emily Kaufman in their 2012 paper. So before moving on to the empirical results, I would like to introduce the baseline, like the state-of-the-art algorithm known for sweeping multi-domain problem. So this was introduced by Kleinberg et al. In the Journal of Machine Learning in 2010. So this was a upper confidence bound based algorithm. So like Claire already introduced, upper confidence based algorithms essentially try to make an optimistic guess about the reward distribution or the mean reward of an arm given its history of observation so far, and that's the algorithm proposed by Kleinberg. This is known as Euler. Okay. So the finite time analysis that I mentioned before has been done by Shipra Agarwal and Emily Kaufman, but only for the classical setting. Also recently, a lot of attention has gone into Thompson sampling because of the empirical evolution by Chappell, where they actually show that the randomized algorithm performs better than optimistic approaches, and there are they are robust to certain scenarios compared to history-based algorithms. So we try to simulate, we try to show our synthetic simulations in line with their work. Alright, so for our simulations, we primarily work with, we only work with synthetic datasets because that lets us control the particular sort of availabilities that we are encountering in order to show that whatever bound we are getting in the theoretically is actually happening empirically as well. So we work with 10 arms and we average over 1,000 independent iterations. The mean of the best arm is considered to be 0.5 and each successive arm has a mean with difference of 0.01. So we concentrate on three particular availability sequences. The first availability sequence is the classical man-to-man setting, where essentially all the arms are always available. The second setting is random availability, where we just assume that each arm is available with a probability half at each point of time. So essentially you can estimate that each arm is available approximately t by 2 number of time steps. And finally we look at another interesting scenario, which is the changing suboptimal arm. That is arm 1, the arm with the best reward distribution is always present. But along with it only one other arm is present, and that keeps changing cyclically. As in arm 1, 2 is present, arm 1, 3 is present, arm 1k and back again at 1, 2. So why we chose these three particular scenarios will be evident in the next slide, where we show our plots. So here we plot the time horizon on the x-axis and the cumulative read rate on the y-axis. So the performance of our algorithm, Thompson sampling for SMAP, is denoted by the red plot, and that of the Euler algorithm, the history-based Euler algorithm, is denoted by the blue line. So as you can see, for each of these availability sequences, our algorithm significantly outperforms the history-based algorithm. So we can we haven't simulated on real world data sets, which we are interested in doing, but synthetically at least we have like worked with a lot of different kinds of parameters, changed the distribution of reward means, try to change the difference of means among different arms, and we have seen that almost always our algorithm performs better. But what our paper presents for the first time is that our paper presents the notion of regret, which is dependent on the availabilities. On all the previous works, they just show a the regret bound for when the availability is adversarial. They don't essentially show how the availability sequences actually influence the regret incurred by your algorithm. So as you can see, like our regret was dependent on logarithmic in terms of AIT, which was the number of times each arm is available. So in the classical map setting, that term goes to T for each arm, and we essentially incur the highest regret denoted by the green line. And in the random availability setting, each arm is present around P by 2 times, so that gives us slight amount of less regret. And in the changing suboptimal arm setting, we had each arm is present around P by K minus 1 times, so that gives us significantly less amount of regret. So in a way, we have been able to capture sort of dependency on how the availability sequences are affecting the regret. We still don't know exactly what is the worst case, or like what class of availability sequences can be called the worst case availability sequences. So that is of particular interest to us. Also, so like building on this, like some of the future work that I'm personally very interested in, like how do we characterize a good or bad availability sequence? Like if we are given the availability sequence beforehand, it's essentially a bipartite graph. On one side you have the set of bandit arms, and on one side you have the tasks, and it's a match. So it's a bipartite graph. So like, can you take some property of the graph and like maybe say like this is a worst case graph, this is a best case graph, or like depending on the structure of the graph, can we somehow add some heuristics to our algorithm to show that this can lead us to better regret. Also the bound that we showed on the bound on the availability specific regret, there's no known lower bound in literature for that. So that would be interesting to find out, which would essentially say that is this the best any algorithm can do, or is there a further scope of optimization. Also, as you saw, the regret terms have a delta term in them, so that those are problem dependent constants. There are problem independent regret bounds for bandit settings for Thompson sampling and PCB algorithms. It might be of theoretical interest to look into problem independent regret bounds, where we can't do as good as logarithmic, but probably root T. And we would like to reproduce our empirical results or real world data sets, essentially conduct a survey on what sort of availabilities we actually encounter in real world. Can we make some further assumptions? And I believe there is a lot of scope for future work. And if somebody has some particular data set in mind that can be properly modified, I would love to hear about that. So yeah, I hope I managed to keep it short and simple. Unfortunately, I don't have a poster, but I will be in the poster session. Please feel free to give your feedback and ask as many questions as you